All right, we're going to continue looking at our recursive patterns here. But first we need to review a little bit some of our exponent rules. So first couple things you might see are just some computational type things, like evaluate the expression. It says to write your answer as a fraction and as a decimal, and to round it to the nearest hundredth when you do a decimal. So the first thing we're going to do is think about what this means. So we have 9/4 to the third power. Remember, that's our exponent. That tells us how many times to take 9/4 times itself. So if I rewrote this, it would be 9/4 times, not 3, but 9/4 and another times 9/4. So I could kind of do that manually and take, remember, when you multiply, just multiply the tops, 9 times 9 times 9, which gives me 729. And multiply the bottoms 4 times 4 times 4, which is 64. And feel free to leave it just like that. Okay, we don't have to write a mixed number. So far I wrote it as a fraction. Okay? And now if I want it as a decimal, well, you grab your calculator. What does our fraction bar mean? Divide. Okay, so I could just divide those two numbers. Another way to do it is to actually use your calculator with the exponents. So let's take our calculators out here and take a look. So those of you that have that same version that I do, that TI-84 Plus Silver, this will work exactly like it. I know some of you, yesterday we had to look, and there's a couple different buttons we hit instead to change from fraction to decimal. So if you have questions on that, don't be afraid to ask me in class. Yeah, so we had 9/4 to the third power. So just like we said, if we want a fraction, we put it in parentheses. Okay. And to get an exponent, there's this little caret button right here. So that gives me an exponent. You see how it makes it nice and small up there? And we want it to the third power. There we go. So now we can just hit enter. Oh, and that actually gave us a mixed number. Remember we set that the other day. When we click mode and we go down, I set that right here. I set it to a mixed number. I can set it back to improper. Okay. But now actually I want my answer as a decimal. So I need to switch from fraction to decimal. And I need to second quit. And now I can just do the exact same thing, and I get it in a decimal. 11.39, and this 0 right here tells me to round down, so I leave it as 11.39. That would be to the nearest hundredth. Yep. So you should be able to use your calculator. Could do it by hand, whatever you prefer. Usually check my calculator just so you get used to using that calculator. Now let's go ahead and apply some of that exponent thinking to a recursive rule. So here we have, it says the stage 0 figure below has a length of 1. At stage 1, each segment has a length of 1/4. Alright, so let's think about this. Let's think about what's actually happening. I'm going to write my recursive rule for this right off the bat. Recursive rule. Remember, the rule just describes what is occurring every single time. Okay, so basically it looks like anytime I have a straight line, I need to remove the middle segment. Well, how big is that middle segment? Oh, look, so this is a fourth, this is a fourth, the whole thing was 1, so if I take away 2/4, that's 2/4 left, which is really a half. So I remove the middle half segment. So that's the first part. Remove middle half segment. Now, the second part's kind of tricky. What did it replace? What did we replace it with? We replaced it with 3 1/4 length segments. We replaced it with segments that are the same size as the outsides. So we can say remove middle half segment for every straight line. Okay, I'm going to add that in there. I'll show you why. For every straight line. Technically every line. I don't really have to say straight. Because lines are straight, aren't they? For every straight line, for every line. And replace it with, well, how do I describe that? It's like going up and then over and then down. It's almost like, kind of like if I continue this on, it's like replace with almost half of a hexagon, right? Of equal lengths. So replace with half of a hexagon with of equal length. That's pretty good. I could probably be more exact, but we just want to get the idea of what being recursive means, that this pattern is repeating. Okay, so why I said for every straight line, so you think about it, we had a straight line, we removed the middle, and we replaced it with half of a hexagon. So if I think about that, when I go to stage 2, that same thing is occurring. Now I'm taking a straight line, for example, right here, and I'm going to remove the middle half. So look at stage 2. There it is. We removed that middle half of that 1/4 segment, and then we replaced it with these guys right here. But the hard part is to think about what size are each of these little segments now. They're not a fourth anymore, right? It's not a fourth anymore, so we got to think. The best thing to do is to create a table, and that actually tells you to do that in your directions. So that's what I'm going to do. I got a table here. We'll come back to B. Don't worry about B for now. So here's my table. So at stage 0. At stage 0, we said that its size is 1, right? It's a total length of 1, okay? And there's no pieces to it, just each thing is 1. Well, at stage 1, all the lengths are 1/4, right? Because we removed the middle, and we added 3 more to make them all 1/4. So here's 1/4. There were 5 little segments, so a total of 5/4. That's the total length. If I added these up, 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4, that's 5/4. So it's really 5/4 to the first power. I could write it as an exponent form as well. Okay? And in decimal, if I actually took 5 divided by 4 to the first power, I end up with 1.25. Right? 1 and 1/4. So that's given to us. Well, what about in stage 2? What about in stage 2? What would each segment be? Remember we talked about they're not a fourth anymore, because we took this 1/4 length and broke it into segments of, what do you think? Fourths of that, right? So like we took this segment, which is a fourth, and we broke it into 5 pieces of fourths again. Well, that's kind of confusing, right? Well, what happens when I take a fourth of a fourth? This should be kind of familiar to what you did the other day. That's a 16th. So each of those segments should be 1/16. And that's represented right here. I know it's kind of confusing. 1/16. So there's 5 of those pieces, right? Of those 1/16. Plus, there's 5 of those segments we did it to. If we look back at stage 1, we did it right here, 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 we're going to do it right here. So look, it happened 5 total times. Right? So that's why it's being multiplied by another 5. So really it's 25 times 1/16 in a way. So that's where that 25/16 comes into play. That's kind of the confusing way to think about it. Right? You know, we kind of explained it all the way through. If you notice the pattern, if we could state that recursive rule right away, if we notice that, with every straight line, you know, we remove the middle and replace it with fourth length segments, and you have 5, like I have 5 fourth length segments, that's going to make things easier. Because if I think about that, it's really just 5 times a fourth, which is 5/4 for the lengths. Well, now that's happening all over again with each of those segments. So in this case, I'm still using that same rule, that 5/4 rule, but what do you think that exponent will be? That's right, to the second power. Okay, so at stage 0, the exponent was 0. At stage 1, when I use that recursive rule of 5/4, right, because I had 5 1/4 length segments, right, that's where that 5/4 comes from. And now the same thing is happening at stage 2, except the exponent is 2. That helps me solve it much quicker than trying to do it the long way. Because now I can take 5 times 5, which is 25. Whoops. Which is 25 over 16. And if I wrote that as a decimal, let's go to our handy-dandy trusty calculator here. 25 divided by 16 gives us 1.56. So we're rounding down, so we'll leave it as 1.56. All right, pop that back up. So 1.56. Very nice. So now I shouldn't have to think through it as much when I do this next section. So if I do it for stage 3, it should make sense. If I do the multiplication form, now I should have 3 5s being multiplied, and guess how many 1/4s? 3 1/4s. And we're just going to skip that part. We're just going to go right to exponent form, or really it's just 5/4 to what power you think? That's right, the third power, which gives me 5 times 5 times 5, which is 125, over 4 times 4 times 4, which is 64. And now we can find the decimal form of that. So go ahead and use your calculator. I won't pop it up this time. And that should give us 1.953, so we'll round down to 1.95. There we go. So now let's go back and answer B. It says, which is the first stage to have length greater than 3? Okay, well here's our total length right here. This is the total length, right? Because the first one had 1, and the other one was 1.25, so on and so forth. None of them have a length greater than 3. So I might have to keep going. I might have to make a table. So stage number, so I left off with stage 3, so I'm going to do stage 4 next. And this can be the length. Well, what's the quickest way to do this? Take 5/4 to what power? Oh yeah, keep going with your pattern, the 4th power, right? We left off with the 3rd power, so now it's the 4th power. And I just keep typing it in my calculator to figure it out. Well, as I keep going, what ends up being the first one that's greater than 3? And I'd probably use decimals because it's easier to see it quicker. So this is about 2.44, so not bad. Stage 5, so I gotta go 5/4 to the 5th power. And that is, there we go, 3.05. So stage 5, whoops, can't spell stage. Stage 5 was the first one that's greater than 3. And continue on to get greater than 10. And it just so happens to be the 11th stage. You'll just have to keep going on your own to figure it out. And because 5 to the 4th, the 11th power is 11.64. So stage 11 here. I did it again. I want to write a G. What's going on there? So there we go. So that one takes a little bit of thought, but once you start realizing that they all have a recursive rule, like a little pattern, it makes things much easier than the way it looks right at the beginning.